Let's talk about this, what we call as quantum step potential. I mean, in quantum physics, the step potential is a fundamental concept, and it's used to describe the behavior of particles in various systems. I mean, it's a simple potential energy profile that consists of two flat regions separated by some sharp potential. And we have potential outside that domain is zero, and between these zero potentials, there is some potential. This potential profile is basically it's used to model a wide range of physical systems, including potential barriers. I mean, the step potential can be used to study the tunneling of particles through potential barrier, a fundamental phenomenon in quantum mechanics. It has its implications in quantum wells. I mean, this step potential can be used to model the confinement of particles in a quantum well, a region of space where the potential energy is lower than that of the surrounding energies. It has implications in heterostructures. I mean, the step potential can be used to study the behavior of particles in heterostructures, which are materials composed of layers with different properties. This step potential is a useful tool for understanding the additional quantum phenomenon like wave particle duality. The step potential can be used to demonstrate the wave like behavior of the particle, such as electrons, as they can tunnel through the potential barriers, which is not possible classically for a particle. And it can be utilized in quantization processes. I mean, this step potential can be used to study the quantization of energy levels in bound states. Reflection and transmission. I mean, the step potential can be used to study the reflection and transmission of the particles at an interface between two sides, between two regions. This step potential is a simple mathematical concept, but still it's a powerful tool for understanding the behavior of the particles in the quantum systems. Its applications are diverse, ranging from electronic devices to optical systems, and it continues to be a fundamental concept in the study of quantum physics. And in this video, we will be discussing the process of step potential. Now, dear students, dear friends, let's talk about the potential step, and and certainly we have a step kind of situation here. We have a particle which is free, then it faces some potential. And if I choose this problem as the problem of one dimension, then then for assuming this to be x equal to 0, where we have the maximum potential. And what this problem basically consists of is that we have a particle, and the particle is free. It is free everywhere, but beyond some particular point. If I assume that point to be for x equal to 0, the potential increases sharply. I mean, this potential is assumed to be the repulsive potential, and this potential increases sharply, and we have a situation here. And what's the situation? We have this potential. This potential is 0, and for x less than 0. So anywhere from x less than 0, this potential is 0, and this potential is equal to say v for x greater or equal to 0. Now, this is a simplest situation here that we are trying to understand. And what we have a particle. This particle is in motion, and it does not face any kind of repulsion up to x equal to 0. And what we try to do here is to analyze the dynamics of the flux of the particles. We can have a particle, we can have more than one particles, and all of these particles assumed to have same mass. These particles have same mass, say m, and they are moving with same velocity. And and this is my left of the situation. Then there's potential, and there's a sharp rise in potential, and then there is the right hand part of this problem. So what we are going to do here is what we do is we will have two cases of interest. The very first case will be that the total energy of this particle is greater than V. It's greater than this V. And in this case, the particles, they are free, okay, and they are free in this region x less than 0, and they are able to feel the repulsion potential that starts at x equal to 0 and stays flat. It stays flat for x greater than 0. And we would like to analyze the dynamics of this flux of particles classically as well as quantum mechanically. Quantum mechanically. And talking about this problem in terms of classical laws, classical physics, the particles that are approaching this potential step, or we may also call it as a barrier potential, from this left, and this is my right of the potential, with some constant momentum. So we have what we have. We can think of E as p squared by 2m, and this p will be under root of twice me. So these particles are moving with this momentum under root of 2me. As the particle enters the region with x equal to 0, or I may put it as x greater or equal to 0, what it faces is the potential. It faces a potential equal to v, and their momentum is slowed down. And their momentum slows down. It slows down to a momentum of, in terms of this equation, we can calculate this as 2m times e minus v. So this is a situation here in terms of the momentum of the particles. But if we go back to this problem, so what's going on here is that these particles they will then conserve this momentum. They will conserve this momentum as they travel towards the right. This is because the particles have sufficient energy to penetrate into the region x greater or equal to 0. Because we are assuming that the energy of the particles that are moving towards this potential step have energy greater than that of this potential. And certainly there will be total transmission. I mean, all the particles that are hitting this potential will make it to the destination. They will go to the other side of this potential, and all the particles will emerge on the right with smaller kinetic energies. If we write down this thing in terms of the kinetic energy, so they will have kinetic energy less than its measure will be E minus V naught, and this is then we can call it a simple kind of scattering kind of problem where a particle is coming and interacting with a field, and there is loss of energy, and thinking about the same problem quantum mechanically. I mean, quantum mechanically, the dynamics of the particles is basically it's basically guided by, or I should say, it is regulated by the Schrodinger's equation, and we can write down Schrodinger's equation. We can write down Schrodinger's equation for the two regions that we have. So if I take region 1, say this is T2 by dx2 of psi 1 of x plus k1 square is equal to 0. So this will be our first equation, and this will be for the region x less than 0. So we're talking about this part of the region. Okay, and in the other part of the region, we will have a different situation. We will have Schrodinger's equation as d2 by dx2 psi 2 of x plus k2 square equal to 0. And out of these two equations, we better understand that this k1 square is twice me by h cross square, and k2 square is going to be 2m e minus v times divided by h cross square. So this is the value of k1 square, and this is the value of k2 square. If we would have started it originally from the time-independent Schrödinger's wave equation. So what we have here is we have a situation. We are trying to treat the problem where the particles that are hitting this barrier, their energies are greater than that of the potential barrier that's being faced by these particles. And in this case, we have two situations. One is we have Schrödinger's wave equation for the particles in this region, the left of the region, and we have Schrödinger's wave equation for the right of the region. And we have written down these equations for the given problem. And we can obviously, we would like to write down the solution of the Schrödinger's equation for the region x less than 0 and for the region x greater or equal to 0. And if we write down the solution here, so for region 1, what I'll have the solution. So in solution for region 1, and we can better understand that these particles are completely free in that region. Their waves are continuous. They have the same amplitude. So we can think of writing down the solution for the left region part as psi 1 of x is a e to the power of I kx plus b e to the power of minus iota k. 1x k1. So k1 we have chosen for region 1, and k2 we have chosen for the region 2. Now for the region 2, psi 2 of x will be c e to the power of I k2x plus d e to the power of minus I k2x. So we can think of writing here, because this is the solution is valid for x less than 0, and this solution is assumed to be valid for x greater or equal to 0. Now, looking for these parameters, I mean so we can translate these mathematical expressions into some words like this: a e to the power of I k1x and c e to the power of I k2x. What they do is they are representative of the waves that are moving in the positive direction. But looking for these negatives of these exponential functions, I mean b e to the power of minus iota k1x, d e to the power of minus iota k2x, they are the representatives of the waves that correspond to the motion of these particles. They are moving in negative direction. And certainly in this case, what we have, the particles are initially incident on this potential. That the situation is like this. Okay, we have a potential V here, and we have these particles they have to hit this potential step from the left, and there are two possibilities that these particles can be transmitted and they can be reflected. So there can be a probability of transmission, and there is a probability of getting reflected at x equal to 0. And if we see this region, this is region 2, and this is region 1, or I call it left region or right region. In the region right, there's no possibility of a reflection of these particles. So to the left, and this constant d must vanish. This whole thing must vanish, and we are surely dealing with its stationary states here, and the complete wave function can be written here. So how can we write down the whole of the wave function for the given problem? And we can write down it, say choosing psi x and t is going to give us psi 1 of x e to the power of minus I omega t, and psi 2 of x e to the power of minus I omega t. And this we can write down as a e to the power of I k1x minus omega t plus b, okay, b is alive, e to the power of minus I k1x plus omega t. Right, and for this situation, d is already understood to have no place in the equation, so we can write down c e to the power of I k2x minus omega t. And certainly this is valid for the region x less than 0, and this is valid for the region x greater than 0. And we can look for this a and the exponential function, b and the exponential function, c and the exponential function. What they do basically is, this is my incident
wave or the particle, then this B is the representative of reflected particles, and this C term is the representative of transmitted waves or particles, because they have the dual nature: transmitted particles, transmitted waves or particles, whatever you feel and whatever you are comfortable with. But certainly we have the dual nature, and we can note down from here that the probability density, if we look for psi of x as whole square, in the left, we can look for it. If we plot down this probability density, so for sure we have a situation here. I mean, the first situation is you have the particles, and these particles are they are going towards this potential, and they have we can write down their wave as ae to the power of iota k1x, and there is a step potential V, and we have energy of these particles greater than that of this V. So it's a situation like this. So we have incident particles, we have reflected particles as BE to the power of minus I K1x, and then we have transmitted particles, CE to the power of IK2x. So this is a situation here for the wave function of these particles, and we can write down the probability density we can write down the probability density for the particles in this region, and the probability density for these particles in this region. So if we write down that, if we try to plot that, what we have is we have a situation like this. So E is greater than V, and we have a point of 0 here, x equal to 0. We have a wave, okay, and there is the transmission. So this is our probability density for psi of x whole square for the particles that have the energy greater than that of V. So what we see here is what we see here is that this probability density that we have in the left side of this plot is it is great. It's straight for x greater than 0. You can see it here. So it's a straight line, and talking about psi 2 of, if we take psi 2 of this x whole square, we have this what we call as the we have this straight line for x greater than 0, and we can calculate, we can evaluate this reflection and transmission coefficient as R and T. And how do we define this reflection R? If I take R as a reflection coefficient, that is the ratio between the current density, the current density that is reflected, divided by current density of the incident particles. So if I have to symbolize this thing, I can think of writing down this R as J reflected divided by J incident. And similarly, we can think of transmission coefficients as J transmitted divided by J incident. So this is how we can think about a reflection coefficient and the transmission coefficient. So this R is what it does basically. It's a representative of the ratio of the reflected to the incident beams, and this T is the ratio of the transmitted to the incident beams. And in order to calculate this T and R, what we need to find this J incident, J reflected, and J transmitted. And as we understand, if we take this psi 1 of x, and what's that? That is, for incident, that is ae to the power of I k1x. we can write down the expression for the calculation of this current density. And what is that? That is J reflected. If J incident would be rather a better idea to start with. Ji, that is going to be IH cross by twice m times psi 1 of x, then d by dx of psi star 1 of x, then we'll have minus psi 1 of x star and d psi by dx. Okay, so we can easily write down this J of I. This is IH cross by 2m. So psi 1 of x is this. So the derivative of psi 1 star. So star means e to the power of minus iota k1x. So on differentiating it, you will have the same exponential function to be multiplied. So here I will have e to the power of I k1x times, okay, the complex conjugate of this function is minus twice I k1, derivative will be the same, e to the power of minus I k1x. Okay, so then we have minus psi 1 star, that means e to the power of I k1x times, we have to take the derivative of the psi, so multiplied by the internal derivative I k1x, e to the power of I k1x. So this is how it will go. I think this thing and this thing will go, this thing and this thing will go. What we are left with is, this is minus, so this is also minus, so Ji will be minus. Let us get it out. So iota will also come out. So minus, so this will become iota times iota will give us iota square h cross by 2m times what will be left here is, you will have minus, why I have 2 here? It's not 2, it has to be I only. There's no 2 in it, so this is minus, minus is plus, so minus we have got out, so it has to be plus. K1 plus K1, that's going to give us twice K1. And this 2 and 2 will cancel. Iota square will give us minus 1, that will be neutralized by this minus, and what you'll be left with is H cross K1 by M. And I forgot to write down A, so you will have A, then you will have A star here, you will have A star here, and you will have A, A here. So you will have A star will give us A square. So finally we will have the square of this constant A. Okay, and similarly in the same fashion we have calculated J1. We can calculate it's not J1, it's Ji. We can calculate J reflected, and J reflected will be minus H cross K1 by M times B square, and you will have J transmitted. The same kind of calculations that have to be done, where you have to take psi of region R, and those symbols are already talked about, and we can calculate that. So here we will have J transmitted, that will come as H cross K2 by M. Then you will have the square of C. And if we keep on combining this JR and JT and JI, we would be able to calculate, as we had defined previously, as a reflection coefficient and transmission coefficient. So all we have to do is to substitute the value of JR and JI in case of reflection coefficient, and JT by JI. And when we do that, what we obtain is, we obtain this R as equal to B whole square by A whole square, and T comes out to be K2 by K1, then C square by A square, magnitude of A square. So these are the two quantities that are measured here using those calculations. And so what we can see here is that that we have reduced down the problem of calculation of R and T merely to the constants, and we can calculate this R and T by simply calculating the constants, and we need to calculate these constants using the boundary conditions of the wave function, and that too at when x is equal to 0. at the point that x is equal to 0. And since both the wave function and its first derivative are continuous at x is equal to 0, I mean psi is continuous, and d psi by dx is continuous at x is equal to 0, we can immediately think of psi 1. So assigning this to be 0 is equal to psi 2 of 0, because there is continuity from this side to this side at x is equal to 0, x equal to 0, and their derivatives like d psi 1 of 0 by dx is equal to d psi 2 of 0 and dx. So in doing so, you're writing down the values for psi 1 at x is equal to 0 from the original equations that we have. We can substitute these values. We can substitute the values for x equal to 0. We will have psi 1 at 0. We will have psi 2 at 0. So in doing that, what we will come up with, it's always important to keep some ground for some kind of vacuum where the student is bound to think and do things. It should not be like spoon feeding. So that's why in any kind of presentation there must be some voids. And these voids should be deliberated by the teachers, so that there is a room there's a room for questions, there's a room for queries, and there is a room for an approach of creative thinking. So in making those boundary conditions, what we simply get is a plus b is equal to c. This comes out to be our first equation, and similarly we get k1 times a minus b equal to k2c, and we can do the simple algebra on these two equations, and we can obtain b as k1 minus k2 by k1 plus k2 times in terms of a, and c we will obtain as twice k1 by k1 plus k2 times a. Now, as far as this constant a is concerned, it can be determined from we can calculate this a from normalization condition. And we better understand what normalization is and how do we calculate the normalization constants. So once the a is calculated and the condition of the wave function, we don't need it here. What we need it here is we can calculate this b and c, and after calculating this with the value of a using the condition of normalization. Now a combination of these two equations, so one has to be realistic here that this a can be calculated. So what we can do here is that the combination of these two equations will lead it will lead to, if we are going to combine these two equations, what we will have is we would like to have their sum basically, and if we choose some kind of simple argument here, I mean if I calculate this r plus t. Now what is my r? R is it is k1 minus k2 divided by k1 plus k2 times then twice k1, plus twice k1 by k1 plus k2. Okay, so both of them have a as a common thing here, and what we can do here is we calculate r is already calculated, and t is also calculated. Okay, and we can add this r and t, and we can see that this addition of r and t will be equal to 1, and this sum of this r and t is equal to 1 as it should be. But in contrast to the classical mechanics, what it states is that none of the particles get reflected. You have a barrier. The energy of the particles that are hitting this barrier is greater than that of the height of this barrier, so they will all pass this. They will all cross this barrier, but here, if we go here, if we write down what we call as the transmission, we have r here, and we are also calculating t here. So calculation of t what it shows is that the quantum mechanics has some reflection coefficient r, and this r should be equal to zero classically, because none of the particles should be able to come back from this barrier, because all of them have this energy greater than that of this barrier. They all cross it ideally, but that's not the case when we treat the same problem quantum mechanically, because it leads to some measurement of the reflection. It leads to the measurement of the reflection. And if it leads to the measurement of the reflection, there are particles that get reflected quantum mechanically, in spite of their energies being higher than that of this V that we have. This effect can be, how can this thing be explained? It can be explained only when we attribute to these particles a kind of wave-like behavior, a wave kind of character. And from the equations of R and T that we have calculated in terms of K1 and in terms of K2, what these equations suggest is that E gets smaller and smaller. As this E gets smaller, T also gets smaller. I mean, we can, because on solving these using these constants in our equations, where we are calculating R and T, which after calculations, what we obtain R equal to K1 minus K2 whole square divided by K1 plus K2 whole square. This is our R, and for T what we have is we have 4K1 K2 divided by K1 plus K2 whole square. So we have transmission probability, we have reflection probability. We have both the probabilities here. And if we add up the two, if we add this R plus T, it's going to give us 1, and that's clear. And what we will have here, K1 minus K2 whole square plus 4 times K1 K2 divided by K1 plus K2 whole square. And here we can open this. If we want, we can write down K1 square plus K2 square minus twice K1 K2 plus 4 times K1 K2 divided by K1 plus K2 whole square. So this will be subtracted to this. What we'll get is we will get this R plus T. R plus T is, we'll get K1 square plus K2 square plus twice K1 K2 whole divided by K1 plus K2 whole square. So this is K1 plus K2 whole square divided by K1 plus K2 whole square. So this is equal to 1. So what is expected here is, if we have a thought, if we encounter what should be the underlying physics for this continuity condition that we have. We can make some observations in our problem. What we have is we have a potential step at x equal to 0, and since the probability density, say psi of x square, of finding the particle in any small region, what it does, we have plotted that graph. It varies continuously from point to point, and the wave function psi must also vary. Therefore, the psi must be a continuous function at x equal to 0, and since the linear momentum must be the continuous function of x as the particle moves from left to right, the first derivative of this wave function must also be continuous at x equal to 0. So to attribute here is, if we attribute a conclusion to this case where the energy of the particles that are hitting this barrier is greater than v, classically, if we think classically, all the particles should pass this barrier. But when we treat the same problem quantum mechanically, there is always a probability of reflection of some of the particles. It's not important that all the particles will cross this barrier quantum mechanically. There is a room for for some percentage, even though that percentage is very less, of the particles to be reflected back from this barrier, and there is quite a good magnitude of measurement of transmission of these particles. So to